Welcome to this online Sesame Colloquium. I hope you're well in all senses of the word. It's a pleasure to introduce today's speaker, Meghna Soni. Meghna very recently finished her doctoral degree at the University of California, Santa Barbara. She received her master's degree there as well. Today we'll be hearing about both of her thesis projects. Before that, Meghna received her bachelor's degree in psychology at UC Irvine, and she's currently teaching at CSU East Bay in the Human Development Department. Meghna works on child and adolescent development with her focus on children's mathematical cognition. Much of her work centers around number lines and how they can contribute to both conceptual and procedural understandings of fractions. These topics are well recognized around here as foundational elements of children's mastery of mathematics, and I hope that today's talk opens up some productive conversation. Please join me in welcoming Meghna Soni as she talks today about improving children's fractional understanding through the use of number line techniques.
Okay, hi everyone. So I'm about to, I'm going to share. Well, I'm going to put my PowerPoint and I'm going to share the screen. So I think that takes a minute for the PowerPoint to load on the screen sharing. And, it's very nice to meet all of you, and I'm really excited for this talk. So let's see the sharing. Okay. 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 So I am very intrigued. Okay, so I forgot to mention this, but if you guys have questions during the talk, it would be, and you can raise your hand, and I think it shows up for me, and I can stop and try to answer your questions. You can also ask questions after the talk as well. So I'm very interested in basically learning tools such as number lines and many tools in general and how they help with understanding of fractions, but also I'm interested in how learning tools will help people with their learning of certain subjects as well. That's very interesting to me. And I worked on doing interventions with number lines and fractions, but I'm very interested in doing interventions in all sorts of things, how learning tools help learning in all sorts of subjects as well. So that's a huge interest of mine. So the work today is improving children's fraction understanding through the use of number line. I'm going to talk about two of my studies. The first one will be the master's. The second one will be my dissertation. And the dissertation was basically, it elaborated on my master's project. So to begin, I'm going to start off with the introduction on the concept. So fractions are challenging concepts for children. They are very important for understanding of greater math, such as algebra and other subjects as well. So they're really important. However, only 13% of fifth graders show proficiency in understanding fractions. So there are many reasons why this is an issue.
Hello.
And one of the reasons why is an issue is because of the whole number bias. And this implies the prior understanding.
Broccoli, just because I was worried about you having vegetables.
You might want to mute.
I think as the host, you can mute everyone else.
You can mute everybody else.
How do you mute everyone?
Excellent.
Wiggle on the Zoom bar. If you click on participants,
Bye.
you can also click on the top right of the picture of the person speaking, and you can click mute. There's like a little drop down. You can click mute person.
Where is mute exactly?
Click on the picture of Jean's iPhone and then drag down. Let's say mute.
Okay, so let's see. Jean's iPhone. Mute. Okay.
Yeah.
Oh.
There we go. It's all you.
Okay. So let's go back. So as I was saying, so for an introduction, I think I talked about how fractions are challenging concepts for children, and that fractions are important for building blocks for other subjects such as algebra. Yet only 13% of fifth graders show proficiency in understanding fractions. So why is this an issue? The first theory is that whole numbers interfere with fraction knowledge, meaning that prior understanding of whole numbers is an issue in terms of understanding fractions. So that's one concept. The other reason is the part whole representation. And the part whole representation is a representation that's predominantly used in classrooms as well to understand fractions. And even though it's considered a good representation, there are issues with it. For example, its inability to show negative numbers. So then my first study tried to look at number line representations as a solution to help children understand fractions. And then the second study looked more on which kind of number lines work best in helping students understand fractions better. Okay, so I'm going to get into the benefits of number line representations. So number lines can be useful for understanding fractions and can be superior to the part-whole method in many ways. Some of the reasons are because they extend the number system beyond whole numbers. You can show all sorts of numbers on the number line. They can also show countless number of fractions on the number line. And you can partition the number line into halves, fourths, and so on. And you can demonstrate how fractions can be divided into smaller and smaller fractions. Even though this is, there's many benefits to this representation, this is not the dominant form used in classrooms. So I was looking at a lot of number line studies, and in many of the number line studies, it was not clear whether the number line was the reason for the students' improvement in terms of their fraction knowledge. And it was also, and the other thing that I found was that many times they only used one number line condition to compare to the control. So there was not much to see if number line was inherently useful regardless of the format it is in. So my first question, and this was for the master's study, is number line successful in improving fraction knowledge regardless of format? So I basically designed a study for this, and I used fourth graders. My reasoning for fourth graders is that's the age where they really get into fractions. And so what I did was I did an intervention study with a pre-test in the beginning and a post-test in the beginning. So there was three conditions: the control, which did just pre-test and post-test. Then one of the conditions was motion math, which was basically an electronic game on the iPad, which used number line. And then there was a paper pencil version, which was the flipbook, which emulated motion math, very similarly, used the same scaffolds, the same types of problems. The only main difference was it wasn't an electronic game. So this is an example of how the motion math game looked. So the participant was given, the people who were put in this group were given a fraction to place on the number line. And if they got it wrong, the game would draw an arrow to point where they think the fraction should be placed. If they got it wrong again, the number line was partitioned into equal parts of the denominator. In this case, it was partitioned into 3 parts. And then if they got it wrong again, a label would show up like 2/3. And then again, if they got it wrong, finally the answer would show up, that 1/3 was placed on where it's supposed to be placed, and it would highlight the answer. So this is actually, I made my paper pencil version to be very similar with the same exact scaffold as motion math. So this is an example of the paper pencil version. For whatever reason, there's a typo here. The 0 is supposed to be in the beginning. Where it says first page, the 0 is supposed to be in the beginning of the number line. But it was something similar where me, the researcher, since the scaffolds aren't built in and I'd have to give them the scaffolds, would say place 1/5 on the number line. If they placed it incorrectly, I'd draw an arrow on where it's supposed to be and tell them to try again. If they got it wrong, I'd flip the page and show them this number line that's segmented into 5 different parts. It's 5 different parts because it's asking for 1/5. So then they'd try again. If they still got it wrong, I'd flip the page and there would be these labels. And then finally, I would show them the answer if they still got it wrong. So these were the different scaffolds for the paper pencil version. The other part of the game was basically where they had to place fractions into 3 bins. Where, for example, they were given this fraction 1/3 and they had to place it into the bin that says less than 1/2, equal to 1/2, and more than 1/2. If they got it correct, the bin would light up bright blue. If they got it incorrect, the bin wouldn't change colors. So that was another part of the game. For the paper pencil version, since I was emulating it to be as closely as possible to the motion math one to make sure that it was more or less the same, I would put something like, is the fraction 1/5 less or equal or more than half? And I'd have a picture of the number line and the bins at the bottom, and they would have to circle whether they think it's less, equal, or more. If they circled yes, I'd say yes. I would say correct. If they circled something else like equal or more, which is incorrect, I'd say incorrect. I didn't give any more feedback because the game did not tell them what the correct answer was. It just said if they were correct or incorrect. Okay, so there was a pre-test and post-test at the end of there was a pre-test and post-test for this study to see how much they improved in their fraction knowledge. So I did a statistical test, and for pre-test, all the mean test scores for all the groups are more or less the same. But if you notice that post-test control did not change much. However, the paper, pencil, and motion math basically showed the same amount of change. They improved both the same amount. As you can see, there was no significant difference between the improvement in paper, pencil, and motion math. So this also is another one that shows the mean gain scores and how much they gained from pre-test to post-test. And as you can see, this is a similar thing because it's showing that the paper, pencil, and motion math are both gained more or less the same, but the control did not gain much at all, which it shouldn't have, but this is showing similar results. Okay, so in addition, I was also curious to see what kind of students benefited the most from this intervention. So I had students who were in the low, medium, and high group, and how I figured that out is they were considered low performing if the student was in the bottom 25% of pre-test scores, high performing if they were in the top 25%, and low performing if they were in the top, if they were in between those. So basically, I was trying to see which performance group improved the most from pre-test to post-test. But as it showed for the paper pencil condition, the low, medium, and high students all improved more or less the same. They all benefited, which was good to see that all kinds of students benefit from this intervention. I did the same thing for the motion math group where I put them in low, medium, and high, use the same criteria for that. And again, it showed that they all improved more or less the same from pre-test to post-test. So all types of students benefited from the motion math intervention as well. Okay, so after the, I was very interested after this, I did the intervention to give them a survey to see how the students felt about the condition they were put in. Like, did they feel that it helped them understand fractions? Did they feel one was more fun or enjoyable than the other? So both groups reported that it helped them understand fractions, both the paper, pencil, number line, which would make sense because the results showed that they improved more or less the same. However, the participants in the motion math condition enjoyed more than participants in the paper pencil condition, which would make sense because it was an electronic game. Electronics would obviously be more fun than a paper pencil condition. So there are many results and implications from this study. So the results and implications are that both the motion math and number line group improved the same from pre-test to post-test as compared to control group. It seems that number line can be useful in improving fraction knowledge regardless of the format presented, since whether it's a digital format or a paper pencil format. and that number line can be used as a tool to supplement traditional classroom instruction. However, motion math is more time efficient because many students can play motion math at the same time and the scaffolds are built into the game. However, the paper pencil number line is just as useful for schools that cannot afford technology, the paper pencil number line may be a good idea. The only thing is that there would be someone who need to flip the page and basically draw on the arrow as a scaffold. But those are some of the implications. And obviously, like any study, there are limitations. One of the limitations is this is a very short intervention. It is not very long. So that is a limitation. Another big limitation is retention is not known. We did not check if after like some months they've still retained the material that they had gained earlier. So we don't know how long they would have retained the material. So this opened up ideas for future research, which means research different number lines, which is my next study. It was also the research of half, of maybe seeing what happens when you use half as a benchmark on the number line, and also maybe comparing these number lines to the part whole method, which is the more popular method. And then this last one, at some point, I'm actually really hoping to do some work on this, and I would love to collaborate with someone on this type of topic because I think it's really interesting, is to maybe have a talk to teachers about number lines and what they know about them and how they think it helps students understand fractions, and to kind of see their perspective on that as well. So that's something that I would love to do in the future. So after doing this study, I decided to do an extension of my first study. So I decided to compare two different number lines to each other to see if one is more effective. So what I basically did was I compared, let me see, let me go actually stay here, but I compared a unidimensional number line to a two-dimensional number line. So the unidimensional number line is just a straight line, which has 0 and 1 as its endpoints. The two-dimensional number line is the kind of the thin rectangle that we saw earlier that was used in my earlier study, which can also have the endpoint 0 to 1, but is in the shape of a rectangle. So I wanted to compare those to each other. And the reason I wanted to do that is even though there's benefits of number line, it's shown that younger students in particular can struggle with unidimensional number lines, or as in just a straight line. And there's many reasons why they could struggle with that. It's not very obvious on number lines when there are, in a straight number line like that there are multiple holes. Unlike a part whole thing, it's easy to see what the multiple holes are, but that's hard on a number line. The other main problem is that many times on the unidimensional number line, if there's tick marks, to find the position on the number line, students actually sometimes count the tick marks other than the spaces. The other issue is many times they're not familiar with the fact that they have to equally divide the number line into equal parts, so proportionality becomes an issue. So this is for the unidimensional number line. So the two-dimensional number line can actually remedy these things. And the main reason why it can remedy these things is, I'll go back to the issues with the unidimensional number line, is a two-dimensional number line can remedy the fact that you maybe can know there's multiple holes, especially if it says 0 to 2, and you can see the whole space and it's easier to visualize multiple holes. The other one is because it's like a part whole representation, you can actually see the actual space become salient, and it's easier to count the spaces in that case. And the other reason is because it's a rectangle, the students know better to partition it into equal parts to find to identify where the fraction is on the number line. So this, the two-dimensional number line basically combines the endpoints of a number line with with a thin rectangle, which is a part whole representation. So what happens in schools is they start off with part whole representations like circles and pies, and then by the time they reach about third grade, sometime in the third or fourth grade, they actually transition to number lines, and then it's just basically a straight unidimensional line, just a straight line. And that's hard because they're going from one representation to another, but this one has its advantages because it can bridge that gap. It has the endpoints of a number line, but also resembles a part whole representation since it's a thin rectangle. So there are empirical evidence for the two-dimensional number line. So Riscon-Sente's study actually used motion math, which utilizes a two-dimensional number line, and the participants in that study improved. Hamden and Gunderson also used a two-dimensional number line, and there was improvement seen there too. And the third one says Soni 2016. That was my study, which both the paper pencil and the electronic used two-dimensional number lines, and the students improved there. So then the research question is a two-dimensional number line better than the unidimensional number line at improving third graders' fraction knowledge? Okay, so I used third graders because for third grade is basically the first time they start getting more introduced to number lines and number lines with fractions before it's all part whole. So I had 3 groups for this one. I had the control, the unidimensional number line, a two-dimensional number line, and there was a 5-day intervention where there was a pre-test, a post-test, and 3 days in between. There was 3 types of questions for the pre-test and post-test, where there was fraction comparison questions, equivalent fraction questions, and placing fractions on a number line. So day 1 had the pre-test and day 5 had the post-test. So for the interventions, for day 2 was the first day of intervention, and students were put into groups and they were introduced, they're basically given a lesson on the number line that they were they were given lessons on the number line group they were put in. For example, if they were in the two-dimensional group, they were given lessons in small groups on the two-dimensional number line. If they were in the unidimensional group, they were given lessons in small groups on the unidimensional number line. Then that same day individually, I had them place fractions on either a two-dimensional number line or a unidimensional number line, depending on what group they were in. Then the next day after that, I actually showed them equivalent fractions on either the two-dimensional number line or the unidimensional number line, depending on what group they were in. Then the 4th day of intervention was just review of the 2 days earlier and what they had learned. The 5th day was just a post-test. So this is an example, and basically this is for the two-dimensional group, and I used the same kind of scaffolds as I used earlier, where if they got it wrong, there was an arrow drawn. If they got it wrong, then segmentation was shown to them, next labels, and then after that, the fraction was shown with an arrow. The unidimensional one was exactly the same and had the exact same scaffolds and segmentations and labels and everything like that. The only difference was that it was a straight line. Just a singular straight line from 0 to 1, but the scaffolds and all the partitions and everything was exactly the same, and even just the arrow pointing on where it was at the end. So those were the 2 conditions. So I did a quantitative analysis on this. So I did a one-way ANOVA, a MANOVA, and a mixed design analysis of variance. So for the one-way ANOVA, both conditions, the unidimensional and two-dimensional condition, as expected, improved more than the control. However, there was a difference between the two-dimensional and unidimensional group in terms of the fact that the two-dimensional group improved the most from pre-test to post-test, more than the unidimensional group. So then I also checked a MANOVA because I was curious between the groups, which one improved more on two-dimensional number line questions and unidimensional number line questions. So what I did was I wanted to see which one improved more. So the two-dimensional group improved more than the unidimensional group on two-dimensional number line questions and, interestingly enough, unidimensional number line questions. So they did better on both types of questions. So the mixed design analysis of variance wanted to see which performance groups improve most on each condition. So for the two-dimensional number line, I also had high, medium, and low performing students. And the same criteria was used as in my last study, where the low performing students were in the bottom 25%. The high performing students were in the top 25%, and in between was 50%. So I wanted to check that out. And for the two-dimensional number line, all performance groups were improved equally from pre-test to post-test for the two-dimensional number line. So the two-dimensional number line was helpful for all performance groups. Though for the unidimensional number line, only the mid-performing groups improved from pre-test to post-test. There was not really any significant improvement for low-performing and for high-performing. So there are many conclusions for this study, and this is that the two-dimensional number line could be useful to implement in curriculum. There's also could be future research could be longer, and again, retention was not checked to check if they retained the information later. And again, there's all sorts of different number lines that can be examined, including ones with certain endpoints, half as a benchmark, and things like that. So there's many different things to do. So the conclusions for both studies is number line is a useful tool to help children understand fractions better. And when comparing the unidimensional to the two-dimensional is superior. However, longer studies should be done in the future, and retention should be checked. Different types of number lines should be tested as well. So thank you. This is basically the end of my presentation. So let me know if you have any questions. I would love to discuss all of this with you now. And I'm also looking for collaboration and open for all kinds of collaboration as well. So this is my email too. So I'm going to stop the share, and then I'm going to open the floor for questions or any thoughts people have. All right, so does anyone have any questions?
I see Morgan's hand up.
Morgan?
Yes, thank you. Thank you so much for sharing. That was wonderful. I hadn't thought about the two-dimensional number line before. I have two questions. One is, do you think it would make sense for children who are in the earlier years, so I'm thinking of kindergarten, first grade, and second grade, who aren't doing fraction work yet, but maybe using a number line for other counting strategies, like counting up? Do you think that the two-dimensional number line over the unidimensional number line is a better fit for them?
You mean for younger kids?
Yeah, even if it's not doing fraction work, just like general, like different counting strategies?
I think it could, because visually it could. I think it's a better, more familiar visual to them. Because I think part of the reason is that kind of visual is a thin rectangle is very familiar to them. Mm-hmm. So I would bet on yes. You never know, but I could guess that it's probably a yes.
Okay. And my other question was about for the two-dimensional, the rectangle. I noticed that there aren't arrows on either end, and I'm wondering about the lack of arrows for students' understandings that it still continues in both directions, on and on. Was that a conversation that you had with students when introducing that kind of number line?
I didn't get into that, but I do get your point that that does make sense, that the arrows that would be something that I would love to test later on, because that would be a limitation of the study, that we didn't focus as much on negative fractions and negative stuff like that. And that without using the arrows, they don't have the idea that it continues on. So that is maybe something that I should have considered, but I guess I didn't for whatever reason. But I would definitely consider it in the future, because I think it would be a great tool to make sure students understand that this, happens, that it actually does continue on. Mm-hmm. So you're right.
Thank you. Thanks so much.
Meghna, hi.
Hi, Dora. How are you doing?
Fine. Good to see you again. Thanks for the presentation. I have a question that is, I'm not sure if it's about theory or methodology, or maybe how theory might inform methodology. And I begin from the point of coming from a sociocultural approach, which I'm not sure if that's something you entertained as you were developing things. Though I did see you cited, for example, the work of Jeff Sachs. We might think of the number line not as a kind of a thing unto itself that it's a it lands running, plug and play, but rather as an artifact that is embedded within certain practices, where we might think of mathematical reasoning itself as a practice. And around that, the object, be it unidimensional or two-dimensional, there are certain routines, certain ways of talking, certain discursive practices, which are probably multimodal, speech, gesture, etc. And so here, between theory and methods, I guess my question is, as we compare students' learning with two or three, doesn't matter, instantiations of this class, which you call number line, right? We would like for our study conditions to everything to be held equal, right?
Yes.
Classical science, classical experiments, so that any difference we see can be attributed to variations in the independent variable which we cared for. So, but at the same time, I kind of wonder what it means to teach with one artifact as compared to the other. And my sense would be that when we use a particular tool, or variation 1 or variation 2 on a particular tool, it is not completely clear to me what, if anything else, has to be adjusted with respect to the way we teach. It could be that we say, oh, I know how to teach with a number line. I'll just use the same gestures and the same way of speaking, the same, right, as I speak about the two-dimensional one, or vice versa. Or we might say, oh, okay, these are kind of different things. They're different ontologies, right? As you said yourself, the two-dimensional one feels kind of like a thing, like a pie or what have you, that has area and
a shape,
like a shape, right? And we know it's almost like manipulable, and it has area, and it's like has stuff. Whereas the number line feels kind of more, it's not like really a thing. It's more like this abstracted mathematical ontology that has no area. It feels more like a tool, something that I would apply to something else. And so I can just imagine, if this is really completely conjectural, it's just a kind of a hunch I have, that if I were teaching fractions with one or the other variation on the number line, I'd probably be using different kind of language, different kind of gestures, different kind of ways of presenting the object and setting the student up for interacting with it in ways that are productive. So that's a very long setup for the question. To the extent that, does this make sense to you? Are these things that you kind of are interested in, which, in kind of a curricular design, this might fall under, the teacher's companion to using the number, all right? Here are things to notice, here are things to do, and there might kind of be little online videos that goes, this is how you might use. So to the extent that you care about these things, can you comment on the methods you used where you probably attempted to keep, hold everything else equal? So what were you trying to keep equal across the conditions?
What I was trying to keep equal across the conditions was the scaffolds were exactly the same. In terms of the fact that the scaffolds, for example, if they placed it wrong the first time, the first scaffold for both of them was to draw an arrow. And then they were segmented the same, and then they were labeled the same too. The only difference was it was a straight line versus a rectangle. But I do get what you're saying, that that when people actually teach this, that you could be talking about it differently. But what I tried to do was, it was just focused on using scaffolds to help them learn, and the scaffolds were put as similarly as possible.
Yeah,
And the language was similar too.
because then it raises the question of the validity or the authenticity of your claims. If you want to say something about teaching, you know, ultimately teachers say, oh, you know, Professor Soni said so and so, so I should do this and that. So do you see my point? It's
Yes,
you know, I could come up with all kinds of analogies for this, but it's ultimately we want to know how this would be in practice when actually you're tailoring your instructional methodology so as to leverage the semiotic potential of these resources. So it seems like your claims are really contingent on the ways that you apply this. So it's
right.
not completely clear whether we can take what the implications for education are from your study.
Yes, I do agree, because I had it very specific. I had a certain script, I had certain scaffolds, but when people are doing it in the classroom, that's completely, they could talk about it completely differently based on what the representation they're showing to the students.
Mm-hmm.
So I think that does kind of have to go with, that would kind of be an interesting thing to see what teachers associate with these representations and how they would teach the different representations as well, because what I did was kind of different. I just focused on the scaffolds and using the same scaffolds each time, but when it's taught in class, that's not how it's typically done. So that would make sense if that answers your question. I'm not.
Yeah, it does. Yeah, thank you.
Yeah. So you're right, there is a limitation there, and that would be a good idea, would be to dive into how the teachers visualize these things and how they see them and how they would introduce them to a classroom.
Mm-hmm.
To actually see if there's really a difference.
Mm-hmm.
At this point, would you offhand have particular thoughts about what you would say to teachers who want to use these ideas in a classroom?
What I would say to them about using them, or asking them about what they know about them.
About using them.
Well, I would say that that I worked with them and that I think both are useful, and that I do believe that the two-dimensional can be more useful, but I would obviously caution it as well, because I'm not sure if my study was 100%, as Dor was saying, realistic in that sense. But yeah, I think I would still tell them to use number line, but I don't know, like now that I'm thinking about it, how I would explain two-dimensional would be better, or how to support those claims as much. If you have any thoughts on that.
If I can just jump in and say a few words.
Go ahead, Carl.
Yes, I have a lot I would like to say. The point about the teachers, it's this thin rectangular shape and number lines, a tape diagram. Those have been used in Japanese classrooms for a long time. I'm teaching fractions. The textbooks actually use tape diagrams. And so, so it's been used in the classroom successfully, and research by one of your former colleagues, Aki Murata, is looking into practices of that sort. So there's evidence that this representation can be used effectively. So that's one point. The other point is that I totally agree that different physical representations invite different ways of thinking, teaching, and people can interpret things differently as well. But one of the points about the, let's say, difference between unidimensional and number lines is that maybe there's this developmental progression that in teaching fractions with younger children, this is something that that bridges between the whole number understanding to the rational number understanding. And this is two-dimensional tape diagram is doing just that. And that's what
Thanks, Yukari. I forgot about that for some reason, the Japanese stuff. I should have included that on my PowerPoint. Hello? Is there any other questions?
I was curious while we have Yukari online.
Yeah, she's my
What
advisor.
what might be the central conceptual structure underlying rational number thinking, and where would that fit? What would Robbie Kay say?
that's a $1 million question, because I've been thinking about it for 20 years. And I haven't gotten an answer for it yet, because Robbie Case and Joan,
Moss.
yeah, they were talking about the rational number central conceptual line would be after children consolidate the whole number understanding. But I actually have a different perspective myself, that children do have some understanding of rational numbers even prior to coming to school. And it's just that their understanding of, say, sharing or proportional reasoning are lost, and because school curriculum really focuses exclusively on whole number understanding or natural number understandings. So what they knew early coming into school somehow is just left there. But if we actually start, or somehow work on their intuitive sense, we may be able to build on the understanding and then make the transition to, or when they need to understand on the whole number to the rational number systems, the transition might be easier. But the other thing is that the other thing I always wonder about is there's one thing to have some conceptual, intuitive, as it might be, but some conceptual understanding of rational numbers. Like if you cut something in half, it's smaller, or anything. But it's one thing to have that, but it's another to somehow understand the notational system. And that, to me, is a huge confusing aspect for children, because we apply all of those the whole number systems, and then using the two numerals, and say, hey, those two put together with a line in between, it actually doesn't talk up, it doesn't show two numbers. It refers to a particular quantity, a particular point on the number line. To me, that is a difficult transition for young children.
And a lot of young children will actually say, if you ask them and they don't know much about fractions, that 1/3 is great. They'll say 1/3 is greater than half, even though that's not true, because they'll say 3 is greater than 2.
And that's their misconception, yeah.
Misconception that takes place as well.
But one of the studies that Meghna, you pointed out to me a long time ago, is somebody interviewed young children who don't know anything about fractional notations, and then they were able to add the numeral and plus some circle or something to show it's more than 1. So if they don't know the notation, they can still come up with their own notation. So that just really tells me that they know something about rational numbers. But just linking it to the numerical notation of fractions is really difficult.
Right. I remember that study. In many cases, they use the idea like age. For example, are you closer to 5 or 4? Are you, or are you 4.5?
Yeah. Mm-hmm.
So that also helps students understand that there were numbers in between 4 and 5, like you're 4.5 or something like that. Okay. He's raising his hand. Dan?
One of the things that I saw done by code.org to teach how the internet works was I would call it a constructivist model. So everybody else in the CS Principles family of classes to teach how the internet worked basically pointed them to videos or took them through, here's this massively complex system that's able to handle you know, a message from A to B gets broken up into pieces, and then those pieces take different routes to get to the destination, and then they get reconfigured and buffered to put in the right order. And if some of the packets got lost, then a message is sent back to, I mean, it's really fascinating, right? It's really fascinating how the internet works and all the procedures of it. But code.org tried the following activity. They, rather than just explain it all, like, here's how the world works, okay? And it's, by the way, it's an engineered system. It's not nature, it's an engineered system. So it's explaining how the engineered system works. What they did was they decided to ask students to create it themselves. What would you do to send a message to somebody across town? There's only one receiver, okay? Fine, you just send the message, okay. Aha, interesting. Well, what happens if, and they would then essentially bring up the difficulties of what happens if the message is too big. Well, we break it up into pieces. And so each of the teacher continued to poke at it and provide difficulties with whatever the current model was. Well, they break it into pieces. Okay, in those pieces. Well, what happens when one of those pieces is gone? How does the receiver know what the total number of pieces that it was intended? How would you get back to the sender that I'm missing a piece? You know, you broke them into 10 pieces. I get a letter that has 9 pieces. Is there somewhere encoded that there were supposed to be 10 pieces? How do I get that message back to the sender? Well, I send a message back to them. What if that message is lost? Right? What if the message that I'm missing piece 8 is lost getting back to the sender? My point of all of this was, it was a mind-blowing way to teach this material, rather than just descriptively explain it, is to have them come up with the protocols themselves. And by the time you were done, you kept bringing up these problems, and the students ended up creating essentially some way, some protocol to handle what exactly happens in the internet today. They have to have an acknowledgement. With the acknowledgement, well, you have to have an ACK of an ACK, and they come up with, they basically engineer the system themselves, and you explain to them, that's actually what the people did. That's actually what the folks who invented the internet did. Amazing, okay? Vince Cerf and all those folks in the early 70s and late 60s. I want to know, and I don't know the research well enough, but I want to ask this general question. Has it ever been done to a student to say, well, you want to give your friend, you don't want to give them 3 cookies. 3 cookies is too few. 4 cookies is too many. You want to give them 3 and a half. And you could say the word a half, okay? But to ask them to come up with, how would you write that down? How would you write down a half? How would you write down a quarter? We're not going to be like before they got any any notation of there's a line and a numerator and a denominator, to ask them, how would you come up with this? What would you create for this? And maybe they themselves come up with a line over a line or something. Maybe they might write 1 out of 2. I don't know how they would do it, but to have them elicit it on their own, I think would be really fascinating. Has that ever been done? That was my question. Sorry for being long on that, but that was it.
Oh, no problem. I think, Yukari?
The study we were talking about, when, 4-year-olds, 5-year-olds, and 4.5, whatever, the interview question asking kids, and can you write it down? And they were able to write, say, 4, and then they bit of oval shaped circle, oval, almost like a little oval next to 4. So they're saying little extras. But as far as we know, there's only one done asking kids to really express their thought. It's more than 4, less than 5. Now, how do you do that? It was 4, and then the little oval shaped thing. And I thought that was so cute. And
yeah, in some cases they put 4 plus, actually.
Yeah, some kids did that. Yeah.
They're like, you're 4.5 years old. How do you show 4.5? They'd put 4 in the ovals, or they'd put 4.5. I think the researcher, I can even send this to everyone, was Barbara Bruzila. I think this was her work, and I've actually read it. It's really good. Mm-hmm. She did that. It was very interesting. In fact, how she was able to get different symbols for half.
I mean, I can imagine I can imagine a young kid drawing a picture of a cookie. If you wanted to actually, I feel like I didn't do this with my own kids. My kids are too old now. But if I had known to think about this just as they were thinking about it, you want to give a 3/4 of a cookie. Do they draw the shape of the cookie? Do they throw like a 3/4 like pie chart, a 4 and a 3/4 pie chart, saying that it's not a full cookie? It'd just be fascinating to see what other things the kids come up with, and if they ever come up with a line, if you could work with them one-on-one to get them kind of like something out of something, if they actually came up with this fractional idea themselves.
What interesting to see if, for example, you want to give your friend 3.5 cookies, if they can visually draw the 3.5 cookies. So that would be an interesting one as well. So people want me to write her name into the chat, Barbara Bruzilla, and I can actually send to everybody what the study was, but that was her name, Barbara Bruzilla.
And then it would be interesting to see whether whatever they come up with changes if you're not talking about cookies, but you're talking about pieces of licorice.
No, exactly, right. Do they do something different if you're going to be sharing? And now it's, what if I want to share you a fraction of like a, like the thing that blows kids away, if you have one of the cups, like a water cooler cup, a cone, a conic shape, half of it is not exactly in the half. It's a lot higher. So like, are they understanding some kind of like a piece of pie? If you're going to give half of a pie, do they cut it from the arc, or do they cut it from the, interesting things of what they come up with if you talk about different things? Is there some general way to be able to share that? Lovely that you could explore that.
Yeah, in terms of sharing something like the pie, and the young children, like I can't remember exactly, like maybe 4-year-olds, they draw a line half, but not exactly half. So one half could be just a teeny bit, the other half could be this big, and then they get better. And it's also, it has something to do with the motor coordination and the conceptual understanding. But it is, somebody actually documented that long time ago, and it's quite interesting how they can you cut in half, and then the one half is just a really teeny bit.
I feel like the potential with this study would be, you have a team of 2 students, and the goal is, your job is to tell, I'm going to show you how much cookie to share, or licorice, or pie, and you need to come up with a way that you can't say it, you have to write it down. And so then, but then you have an agreement of what's the protocol of you both need to teach each other and work together to come up with an arrangement, like a communication model of how you might share that idea. This, what's crazy, this brings up, at some point I got a chance to see when they sent up, oh gosh, I don't know how this one, they sent up a gold record. There's something they sent into space, which was, here is who we are as a humanity. And they sent a recording of Louis Armstrong and some other things, but they tried to encode. Imagine if this is going to be read by, extraterrestrials. They try to encode numbers, right? It's almost like you're coming up with an encoding of this fractional element, which is similar to us sending something out of space of what our numbers are and what pi is and how you, like, who knows? They obviously don't speak English. So what they came up with was fascinating. And I should find a link to that, but it was really fascinating what they came up with as what they sent in. Similar kind of thing, what the kids would come up with, of like how to make the protocol of be able to pass information back and forth. Love it.
Who was Morgan raising her hand?
Christina can go, because I already shared. Go ahead, Christina.
Hi. Thank you so much for the talk. I had to, like, the last minute or something, I had to look after my kids, so I hope I didn't miss that. It would be pretty embarrassing, but I'm asking right now. I was just wondering, all this talk right now about communication and formalization make me wonder, so the students got the correct answer better in the end. So that was kind of like in the
test and post-test was kind of seeing.
Exactly. So what do you think, and how far would this approach to fractions change the response of the students if you would ask, what is a fraction?
You mean how they would think, like if you just ask them what a fraction was versus showing them number lines and placing them?
I don't know, like in comparison to the whole part of a whole approach or part of several whole approaches, where they often respond to, like, it's they have an idea of this concrete context. Is this like a part of a pizza or part of it? And I don't know how easy it is to, well, what they would respond if their first approach to fraction would be something that is, well, it is kind of the part whole concept is embedded into this rectangle. But I would be curious about what they would, how they conceptualize the fractions if they have that approach as a first approach instead of the part of a whole approach.
Well, the thing is, if you do use it first, I still think part whole is a good approach. It might still be a good idea to kind of use it because it's very good context, even though it has some drawbacks. There are some benefits as well. But I think if you see as for the two-dimensional number line, it would be easy for them to conceptualize this as a Kit Kat or candy bar even. They could see it that way, that this is half of the candy bar, this is 1/4 of the candy bar, the whole, this is 1/2 of a candy bar, etc., etc. I think they could conceptualize that way, if that's what you're asking. If they could see, if they, because a rectangle is a common shape to them. Now, in terms of the number line, as in the straight line, that's very difficult. It would be very hard to tell them to conceptualize that because it just is not really an everyday conceptualizer. If that makes any sense. I don't know if I answered your question well enough.
Yeah, I think so. I understood the number line as a part of as a first approach to fractions, not as an additional approach.
It may not be a good idea to use it first. It might be good to still go with part whole, then to transition to two-dimensional, then transition to just a single number line.
I see.
Because I'm still not sure. If you do want to use number line first, I would think that the two-dimensional is better to use because it still is a shape, and that's still easier than just a single line. That's something that I don't know if I helped answer your question.
Maybe. Thank you.
Oh, did I answer your question?
Probably, yeah. Thank you.
Let's see. Does Yukari? Let me see if Yukari has any feedback to that one. Is Yukari here?
Yeah, I'm still here. Yeah. What's your question again?
Chris, you can give her your question as well.
Yeah.
I think it was responded. I think I was a little bit confused in the beginning because there was something about superiority of the one method over the other. And I think that kind of confused me about the approach, which would be a superior approach to fractions or not. I think maybe I just misunderstood that in the presentation.
I don't know if this answers your question, but rational numbers have multiple meanings, and a part whole is just one of them, you know, and a ratio and a measure and all these different ways of thinking about rational numbers. And if we teach children the part whole only, then like Meghna said at the beginning, that it has a number of limitations. For example, it doesn't extend. It's always dealing with some sort of an object, discrete or continuous, some sort of object. And oftentimes in a part whole, it doesn't really extend, whereas number line does. In her study, she did not extend it didn't have the arrows for the two-dimensional number lines, but the implication is that number line does extend in either direction, whereas in a part whole seems to be focused on whole number understanding, really. So it's just one of the interpretations of rational numbers. Again, like Meghna said, it is a useful way to think about it, but that's not the only way. And the problem that we see in the classroom is that oftentimes that's the only representation used to talk about fractions. And so I think it's better to have multiple representations, and always good to have multiple representations, right? And develop multiple meanings, and then make connections, conceptual links among them, you know. So this is just one way to say, hey, there's more to fractions than just the part whole.
Yeah, so the part whole doesn't necessarily need to be replaced. It just needs to have different representations and maybe more emphasis on number line than there is, if that makes any sense. We're not saying that part whole is completely bad and needs to be replaced. It's just saying that there's too much focus on that, and maybe they should focus on other ones as well, and other ones that have certain advantages the part whole doesn't. But by no means would I say the part whole should be taken out completely. I don't advocate for that, if that makes sense.
Yeah, that was just the superiority on one slide, which kind of really threw me off.
Yeah, sorry. It was just trying to say that there was more, there was some drawbacks to that, and there was some superiority for the other one as well. But it didn't mean that there was no benefits to the part whole, if that makes sense.
Just an interesting story. It's just a background, but when I was working with Bob Siegler and Tom Carpenter and all that group, a bunch of people developing a practice guide for fraction instructions. That's 2010 publication. Bob Siegler was so big on number line, and so he was saying the number line is the representation in teaching fractions, whereas Carpenter is like, no, that's one of the representations. So in the end, we decided the number line should be a representation to use in teaching fractions. So that was quite a bit of an discussion, and I enjoyed participating in it.
Number line is definitely a newer representation for sure. That's for sure. Any other questions?
Perhaps not so much a question, just a quick comment to bring together a few of the strands, and that is that it is known in cognitive developmental psychology research of mathematical concepts that there's more than one. There are several developmental resources for making sense ultimately of mathematical concepts. And some of them pertain more to what is called in the field spatial reasoning, and others more to, I guess, discrete reasoning and practice of enumeration, and counting, etc. And we should realize as designers, teachers, researchers, when we just look at something like a number line, we already bringing to bear very advanced, complex, integrated schemes, or whatever you want to call it, depending what theory you come from. But we bring integrated, coordinated resources that enable us to engage in this practice of using a number line to think about this, to think about that, etc. Whereas when children are learning, they need to do that work, the work that now we are experts in. They need to do that work of first coordinating between spatial reasoning and quantification. The number line is an artifact whose use calls for the integrated bringing forth of both spatial reasoning and discrete reasoning related to quantities. For us, it is so obvious that some kind of spatial extension is used in practices related to determining and articulating quantity. But for children, it is not the case. They have and as Yukari was saying earlier, they have different resources, and some of them are just never leveraged and kind of quashed, and only eventually they come back to them. And that's in the work of Lien Verschaffel and the whole, the Belgian group with De Korte and others. They talk about the kind of the U-shaped progressions where kids in school, they come in originally, they have this proportional resources, but like curriculum says, oh, no, we're going to start with counting and discrete and these kind of things. And then later they reintroduced into the proportional reasoning, but now coming from this formal school thinking, they just don't have handles on what was such a rich evolutionary primordial this ancient capacity that we have to reason proportionately. And so the irony is that they get the proportion wrong, and then, well, it's a whole developmental story, because then they start overproducing with the proportional reason until they kind of find the balance. So I think Verschaffel's group called one of their papers to something like from proportion to this or that and back again. So this is it's really a comment that to the extent that you wish to develop this line of research, I would heartily recommend to look at work such as by Stan Dehane and other people who are doing deep quantitative studies of young children's early developmental resources for thinking quantitatively, to think of learning as the integration of the more spatial and more enumerative types of reasoning. And just always to remember that what's so easy and obvious for you is not something that is early obvious to students.
Right. Who was the name of the researcher?
Well, I mentioned a few people. One of them was Stan Dehane. One of the most important cognitive developmental psychologists looking at the growth of quantitative reasoning. And in passing, I mentioned the name of Verschaffel, and I'm sure Yukari can follow up with you with the difficult spelling of that word, yeah. That name. And I can also follow up with you by email later.
Yes, yeah, I can email you, and it'd be good to know these names because I'd be really interested in it.
Oh, and one more important name in this regard is Susan Levine.
Susan, oh, I think I've read something by her.
Yeah, with Ty Boiler and so on. Yeah.
Oh yes, I think that I have a feeling that I know her.
Okay, and going back to when I was writing my master's, Peter Bryant.
Oh yes.
Yeah, I've seen some of these.
And his work with Spinillo.
Mm-hmm. 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 Some of these names are very familiar. Mm-hmm. So does anyone have any other questions they'd like to ask? There was somebody who was raising their hand earlier before Christina, but I don't remember their name. Who was that?
It was me, but my question was answered. It was about scaffolding, and it was discussed. So thank you so much.
Okay, you're sure? Okay. Anyone else? Would anyone else like to take the floor, or have any questions or thoughts? Okay, Dan.
So I feel like there's a 600-pound elephant in the room, which is that the whole world has been thrown to this online space, and all the things that used to be face-to-face, all the activities that were, a teacher sits over your shoulder and works you through learning the number line is now thrown to the winds, and there are videos and online activities, and
games
and apps and games, and also to try to do the same thing. And I feel that your first result, which showed that there was an equivalence of performance of the students if you sat over their shoulder and worked with them on paper how to teach them the number line versus using an app to do that, was a positive one. And I think there's an incredible opportunity to find out what things are able to move online in terms of students. Who knows what kind of autodidacts they are at that young age, but how many young kids could actually use an app and learn it just as well as if it's a one-on-one teacher were helping them using whatever resources they wanted to work with face-to-face. What's the effectiveness, what's the loss of effectiveness as we all are being thrown into an online model for the spring and the summer and maybe even the fall? So just to hear that maybe learning the number line can work in the equivalence of the scaffolding you would have done with a student with your flipping the charts versus the app, that's great. What other things, what's the kind of loss? What's the loss of other elements for different age group? I think is an open question.
To see if for certain things, if there's a loss, if you make it online versus you do it face-to-face.
And trying to keep the equivalency, like trying to keep as much as you would have done, whatever you would have done in a face-to-face, you try to have an app that does exactly the same thing and corrects you in the gentle way that a teacher would have.
The same, which was good.
Yeah.
I don't know if it would hold up in every single learning assessment.
Right.
Like
you've also got the meta point that the kid might get uninterested by the app or get more interested by the app. Like, there's something about
a little bit of
the gamification can change different things in terms of.
Because it was a game, people were more excited actually.
Right.
So that could have made up for the lack of person being there, that they were very excited to play the game. Right. And the good thing with the app is this is a very good thing in the classroom. If the teacher has what they call iPads, You can just give the whole classroom iPads and they play the game and the scaffolds are built in versus getting each student individually to work with someone.
Right.
So the efficiency is definitely great that way. There's no doubt about that. That if you can actually get equivalent results using a game that has built-in scaffolds, that's great, because then the efficiency goes up completely, because you can tell these kids, okay, let's play motion math. All of you take your iPads out. Let's play it for 15 minutes versus let's all go one-on-one and work with me. Kind of.
Right. And I'm sure there are lots of kids who they get on a rhythm and they get, I got 8 in a row. Don't take my, give me more time with motion math. I'm having fun here,
It was more fun to them. That
Right,
was no
right.
doubt that it was that some of the kids were actually were basically, for example, when the student got it correct, I'd say correct or something, but it was very exciting when the computer was like correct.
Yeah. Exactly.
There was also that kind of feedback too.
There's a meta piece, which is my son and daughter both have done Khan Academy, and there's a time where Khan Academy is a little bit too transparent in letting you know how you move and progress through the system. And if you mess up one thing, that you have to get like 5 or 6 right in a row, and if you mess one thing up, that you have to then go back and do 5 more. Like you don't get to up level to show one more level of mastery. If you get one, if you just type something wrong, or if the thing is brittle and you type it wants 5.5, but you have to type 5 and then click the fraction to type 1/2. My daughter is going through this a little bit now, and what she says is she rage quits it. She actually has a word called rage quitting, where I was learning it, having a good time, and then this thing was brittle. I gave the answer. I know what the heck it's 5.5, but I typed it in a wrong formula that you wanted. And they actually found some bugs as well. And I got so angry that now I had to go repeat the silly thing 5 times in a row. I rage quit it. So there's a whole social psychological element to using these games where, if I tell you that now I'm sorry, you've now lost time. You've lost credit. You had 4 in a row and you missed the 5th one. Now you got to go back and do all 5 again to prove mastery. She got really frustrated.
Yeah. The thing with this game is the reason we also did 4th graders is they have a little bit more fraction knowledge, and to do the game, it was required that they would have some sort of understanding. So that's because otherwise, if they were starting fractions from the beginning, it would not have been a good idea to just give them a game. That's why we started with 4th grade versus maybe 3rd grade, because 3rd grade, they do know fractions, but since they're starting, doing a game might have been more daunting for them, if that makes sense. Okay, so are there any more questions from anyone? Or someone who... Christina? Oh, you're showing up on my screen. Do you have a question?
No, I just, my something broke down. I just had to re-enter. Maybe that's why.
Okay, does anyone else have any questions? Because I think there's a lot more people on this chat, and some people have been sending messages to me. Who is it? Someone called Maya sent me a message, and there was other people too. So do any of those other people have questions? Okay, doesn't...
I have a question.
Okay.
I'm curious just about the logistics of motion math. I'm I'm going to be a teacher next year, as well as several of my peers here. And I was wondering, how available is it? If it's free to access, if the district has to buy it, if the school has to buy it, like what about its accessibility.
Well, it's when I first was doing the study, you did have to pay for the app. So I did pay for the app and a couple iPads. It wasn't too expensive, $3.99 for an iPad. But I think they do have, I'd have to double check. And if you want, you can even email me and I can check for you. They do have a motion math thing where you can sign in as a teacher and they can use it for at least some period of time for free, I think. So I think that is something as well. And I do want to emphasize that the motion math thing I used, this was fractions, but they have many different games for motion math. Yeah. Plenty of games. Like, it's not just for fractions. There's so many. So does that answer your question?
Yes, thank you.
Okay. So does anyone have any thoughts or other questions as well? Anyone else? Any comments, thoughts, questions, or anything like that?
Thank you so much. Thank you for giving us the space to talk about fractions and number lines. I learned a lot. So I just want to say thank you.
That's great. I'm really happy.
Yep. Thank you very much. It was great.
So much.
That was great. Thank you so much.
Looking forward to using two-dimensional number lines in my 4th grade classroom.
Amazing. That's amazing.
Bye-bye.
Bye.
Okay, thank you. Thank you.
Thank you.